All right, good morning. We're talking acids and bases. Are you ready? So before we start, let's review some concepts because there's some things that you should understand before we get into this concept. First of all, cations are positive and anions are negative. So I remember it, cations, meow, are positive. And I remember anion by looking at a negative ion. Okay, so cations are positive. Also, cation, do you see this T right here? It's like a plus sign. All right, so there's some reminders. Water is polar. What that means is the electrons are not shared equally. There's an unequal little tug of war happening. And those electrons are pulled more tightly toward oxygen, which ends up with a partially, this symbol means partially, negative charge. That means the electrons are pulled slightly more away from hydrogen, so it ends up partially positive, both hydrogens. So this end of water is partially negative, and this end with the hydrogens is partially positive. And that gives water a lot of unique properties because although it is not ionic meaning the electrons are completely transferred and we have cations and anions, there are still positive and negative parts of the water molecule itself, so that gives it some uniqueness. One of those things is that ions from ionic compounds, when they dissolve in water, have water molecules arranged around them in a certain way. So sodium right here, sodium ion is positive. It's a cation. So the negative oxygens are going to arrange themselves closer to the positive because negatives and positives attract. Whereas the chloride ion right here is negative. So the positive hydrogen end of water is going to arrange itself closer to chlorine. Something else to know, electricity, when you flip on the switch, when you have a battery in a flashlight or your phone, it's from moving electrons. Okay, so remember this, electrons are the ones that are moving around. The protons, not the neutrons. Electrons are moving. A conductor. A conductor means it allows electricity to flow through it. So we usually think about metals. Okay, so if you hook a metal in an electric circuit, the light bulb will still light up. An electrolyte is something that conducts electricity if you dissolve it in water. Okay, so we do have strong electrolytes versus weak electrolytes. So you see this strong electrolytes, strong acids, strong bases, but every single salt. I don't care what kind of salt it is, sodium chloride, potassium chromate, doesn't matter. If it's a salt, it's a strong electrolyte. And then for weak electrolytes, we have weak acids and weak bases. But this is part of the conversation in this unit in particular. All right, well, strong versus weak electrolyte. So weak electrolytes, if you look, still conduct electricity. So you see that light bulb still lights up, just not as bright. Strong electrolyte, super light, super lit up, okay? Conducts electricity well. And if you look at the solution, so a non-electrolyte, do you see this? I don't see any positives or negatives in that water. I dissolved sugar in there, for example. A weak electrolyte, do you see I've got some positives, some negatives? So I've got some electrons able to be moving. Strong electrolyte, do you see how many more I have? Okay, and then a strong conductor versus a weak conductor. Similar concept. It's going to be a strong conductor when it has a bright light bulb, a weak conductor when it is more dimly lit. All right, so strong versus weak electrolyte. Again, so strong conductors, strong electrolytes, brightly lit bulb. Weak conductors, weak electrolytes, more dimly lit. All right, so acids and bases. Here are some properties that we're going to be talking about. So just to give you an overview, but let's get into it. So acids, a lot of things around us. A lot of foods are acidic, okay? And you may have seen some of these names before, like lactic acid, like citric acid, like ascorbic acid. You may be familiar with some of them. Some common acids, again, it's in a lot of food, so you may be familiar with a lot of these acids. Hopefully not battery acid, please. Okay, so I said most of these, there's a lot of acids in food, but not all acids are edible, so please do not misinterpret that statement. But vinegar, lemon juice, soda, you can see lots of examples. Okay, acids are conductors. They conduct electricity. And again, you see this? It's because of the positives and negatives. But they can be strong or weak conductors, strong or weak electrolytes. So you can see when there is a strong acid, we have lots of ions around, and we have a weak acid, we have less. So when you mix an acid in water, it breaks apart into its ions. When you have a strong acid, it completely dissociates. They all separate into their ions. And when you have a weak acid, only some do. So it's less strong of an electrolyte, less strong of a conductor. Acids react with many metals. Okay, I've done a magnesium strip and hydrochloric acid many times in lab. Hopefully you'll do something like that too. But it does create hydrogen gas, and you can ignite that gas. It's kind of fun. All right, so acids react with many metals, and we will talk about this when we get into our next unit, which is oxidation and reduction. So what about bases? Well, bases, a lot of bases are cleaning, all right? And acids don't have a particular feel, but they do taste sour, again, but all acids you do not want to taste because battery acid falls in that category. Bases usually don't want to taste either, but they taste bitter, okay? Bases also feel slippery, soap, okay? Like acids, bases also conduct electricity, but they fall under that same guideline. If we have a strong base, it completely dissociates and it conducts electricity very well. If we have a weak base, only some of the ions dissociate and it doesn't conduct electricity as well, but it still does conduct electricity. Okay, so table K. You get this reference table. It's beautiful. It's a gift. But there is something that you need to know about it that's not written there. So you can see what I put right here. The strong conductors and strong electrolytes are at the top of the table. And the weak electrolytes and the weak conductors are at the bottom of the table. So this one right here I'm going to talk about. See this carbonic acid? That's in soda. It makes sense that it's not a strong acid because it's in soda. Okay, how do I know that's the one that's in soda? You see this CO2 aqueous, that means CO2 gas dissolved in water, the bubbles, okay? And this one, acetic acid, that's vinegar, okay? So which acid is stronger, sulfuric acid or sulfurous acid? Which one is stronger? Sulfurous, right? It's closer to the top. What is another name for acetic acid? Ethanoic acid. And you can see that carbonic acid has two ways we can write it, and so does ethanoic and acetic acid. So be careful of that when you're asked questions because the name of the compound or the chemical formula of the compound could be either one. Which acid is found in soda? Do you remember? I talked about it. Yeah, carbonic acid. Now let's look at table L. Okay, same guideline. Strong electrolytes, strong conductors at the top of the table. Weak electrolytes, weak conductors at the bottom. Now on this table, there's only one weak base. And kind of think of the Sesame Street song, one of these things is not like the others. Can you guess what the only weak base is? Yeah, it's ammonia, because look at what all these have. OH, OH, OH. Okay, that's the only weak one. There are two acid-base theories. There's the Arrhenius theory, and the Arrhenius theory says acids form H pluses as the only positive ion in solution, and bases release OH negatives as the only negative ion in solution. But something to remember, all acids have H's, H pluses, and OH negatives. Bases have H pluses and OH negatives. Bases just have more OHs, and acids have more H pluses. We'll talk about this later. The Bronsted-Lowry theory doesn't talk about OHs at all. It just says acids are H pluses or proton donators. They're giving them away. You get an H plus, 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 you get an H plus. And Bronsted-Lowry bases are H plus or proton acceptors. Thank you. Now, what about buffers? Okay, you don't really need to know a lot about this, but I do like to introduce it. A buffer is something that resists a large change in pH. So if I add some acid, the pH doesn't change a huge amount. If I add some base, the pH doesn't change a huge amount because I have some things already in the solution that are going to resist those changes. Blood is one of the things that is a buffer, and the reason is a dramatic change in pH would have serious consequences, including death. Okay, so you can see the pH range for what's normal for us is 7.35 to 7.45. That's like itty bitty. Okay, if we go above that, it's alkalosis, so like alkaline, and if we go below that, it's acidosis, like acidic. Okay, but we have ions, we have compounds, we have chemicals, however you want to think about it, in our blood, which resist changes. So if we drink a bunch of lemon juice, or we had some antacids, so we ate some Tums because we had a stomach ache. We have something in our blood to help kind of negate those changes, so our blood pH doesn't change too dramatically. If our respiration rate increases or decreases, because that involves CO2 being in our blood, it can also change the pH of our blood. So there's a lot of things that can change it, and most of the time our blood is really good at resisting those changes because it is a buffer, okay? And there you have it. That is an introduction to pretty much most of what we're going to talk about in this unit. So I hope you learned something new today.